Alright, here we go. You all have been requesting this video for quite some time, and fortunately, we've already discussed time series analysis and its place in quantitative finance on this channel, so we are prepared to discuss one of the most profound and innovative models in the entire space, and that is this ARCH and GARCH volatility model or process pioneered by Nobelist Robert Engle in 1982. I actually had the opportunity to watch Robert Engle give the keynote talk at a Bloomberg Quant seminar. It was a very cool experience. I learned a lot, got to meet a lot of very interesting people at those Quant seminars. I even gave a few lightning talks of my own. So if you have access to a Bloomberg terminal, you'll be able to look up those lightning talks and see the different presentations that I gave at those seminars. But I'll digress for now. In any case, very excited to be able to discuss these models today. The best way to go about understanding these models is to understand why they're necessary from the standpoint of the dynamics that we need to capture. So what we'll do is we'll discuss volatility in general. We'll discuss realized volatility and implied volatility, similarities and differences. We'll discuss relevant statistics, applications of volatility modeling, and some stylized facts, things we observe in the market that volatility tends to do, and relationships with returns. We'll then move on to this idea of modeling volatility in a pre-ARCH world, before this ARCH model was even conceptualized. Then we'll extend to a post-ARCH world. We'll go about modeling volatility using such a process. Then we'll extend to the generalization, this so-called GARCH model, and talk about the impact in the applications. Very rarely in quant finance is anything constant over time, but what directly contradicts this and is always constant over time is access to my Jupyter Notebooks. This Jupyter Notebook will be linked in the description below. I will also post it on the Quant Guild library on GitHub, where you can find all of my Jupyter Notebooks and associated YouTube videos, along with the source code for all of my quant builds. At the top of this Jupyter Notebook, you'll notice some related Quant Guild videos on topics applying statistics to trading and finance, working with different measures of volatility, realized volatility, implied volatility, time series analysis specifically for quantitative finance, the different tasks we can perform, different decompositions, and the impact in this space. If you're unfamiliar with any of these ideas, I highly recommend you check these videos out first before approaching this one on the ARCH and GARCH models. Moreover, these videos certainly take a lot of effort to create, so if you'd like to help support the channel, please like, comment, subscribe, check out channel membership. It helps me out a ton. It is so greatly appreciated. And if you'd like to master your quantitative skills, check out quantguild.com. Maybe you come from a background in business, economics, computer science, and aren't too sure where to start on your quant journey. Quantitative finance is such an interdisciplinary subject, combining so many ideas from math, computer science, finance, statistics, probability. It's hard to figure out where to get started. Well, Quant Guild is for you. We have over 90 quant lessons from the ground up in math, probability, and finance, an adaptive practice engine that scales with your skill level, gamified rank-based progress so you can progress to more and more difficult questions, interview questions with fully worked solutions, trading games, coming soon, courses in coding, math, statistics, all from the ground up. And all that's included with Quant Guild membership. And you can get started right now for free. So if you'd like to help support the channel and master your quantitative skills, check out quantguild.com. Without further ado, let's get started by discussing this idea of volatility. What is volatility anyway? We'll hear this as some sort of fear gauge, some measure of dispersion or choppiness. All that's a very fair assessment. Really, a little more formally, all volatility is a measure of deviation from some sort of expectation, typically in the context of returns. So we're not dealing with the stock price path, but rather the returns associated with that path. And things get tricky here really quickly because immediately we are confronted with a question. What is the expectation? We can't just go out into the market and observe volatility. We need to create some sort of benchmark expectation that we're measuring fluctuations around and deviations away from. So what should that be? Well, one way to go about constructing a benchmark is to get a whole bunch of historic return data, compute the average, and then measure deviations away from that average and use that as volatility. Effectively, that's what I do here. So this is what we would consider realized or historic volatility. I'm getting Apple return data, I'm taking the average return, and then I'm measuring deviations in the returns about that average. So anytime there's a deviation on the downside or the upside, I measure that distance, I compute that as a volatility. It's the squared deviations here. So on the left, you see the returns. On the right, you see these volatility measures. Why are they different and why are they changing over time? Well, volatility is not constant. Volatility is going to change over time. It's a very, very important thing to note about this latent process, this unobservable process. Moreover, when we use different time periods to measure the benchmark, you can see that the subsequent volatility measure also changes. So what I have here is I have two of the same time periods and one different time period. I'm querying this data from Interactive Brokers, their trader workstation. I'll leave a link in the description below if you'd like to get started with them. I highly recommend Interactive Brokers. Been trading with them for over 10 years in an investment algo trading capacity. I highly recommend their API. So if you'd like to get started, I'll leave a link in the description below. Nevertheless, I'm pulling the 30-day realized or historic volatility directly from Interactive Brokers. That's this green path. And I'm also computing it myself. And you can see there's a little bit of a discrepancy. There may be a slight difference in the computation, but they certainly track very closely. So in terms of a realized volatility measure, I'd say I'm doing a pretty darn good job of tracking, say, that green line. Okay, and that's just by simply looking backwards, computing this expectation, this benchmark, and measuring deviations around it on a rolling 30-day basis. So every 30 days, I'm going to take the average, then I'm going to measure deviations, and I'm going to roll that forward by 1 day, take the new average, roll that forward, so on and so forth. You can see that those paths are much smoother than the red path. The red path is going to be more volatile because I'm not using as long of a period to measure the return. So the benchmark that I'm using to measure deviations around is rolling at a much faster time window than the 30-day. So it's capturing more of those wild swings because the benchmark isn't as smooth as the longer time horizon. So this is what realized or historic volatility would look like. But I thought historic data wasn't indicative of future performance. You're right, it's not. There's nothing that says this benchmark is going to hold in a forward-looking sense. In fact, we can see volatility changes very quickly over time in each of these cases, right? We don't just have a constant volatility measure here. That's not something that we observe in the market. Volatility is certainly time varying. Nevertheless, when it comes to producing a measure of backward-looking volatility, these types of techniques definitely tend to suffice. But what about forward-looking volatility? If we're observing, let's say at this point in time, let's say this is today, we're observing like a 13% realized volatility. Is that fair to say? So that's on a 30-day rolling basis. Is that fair to say we're going to see similar volatility for the next 30 days? Or should we use a different measure? Is there a better forward-looking measure? There certainly is. And that brings us to implied volatility. Now, implied volatility is very interesting because it directly comes from the options markets, directly comes from inverting the Black-Scholes model. So I have a lot of videos discussing the Black-Scholes equation, the subsequent solution, the Black-Scholes model. I highly recommend you check those out if you're interested. I'm not going to do a deep dive into that topic herein. Rather, we're going to use the Black-Scholes model to come up with this implied volatility. So how do we do that? Well, given the Black-Scholes model, what we can do is we can use the market option price to back out the volatility required to produce the prices observed in the market. And that volatility required is the so-called implied volatility. And what this is essentially what traders are pricing volatility at in a forward-looking sense. So in terms of volatility to come, this is literally what the market is pricing options that are expiring in the future at, given the level of volatility. And that again is found by inverting the Black-Scholes model, finding a solution to this minimization problem. So what are we looking at here? Well, we're looking at a very important chart. This is going to make the distinction between a backward-looking measure of volatility and a forward-looking measure of volatility. What you can see here is we have implied volatility and 30-day realized volatility. Now, at any point in time, I can go into the market and I can observe what implied volatility is at right now. And there may be some aggregate composite measure, but typically implied volatility is quoted for a particular moneyness and a particular maturity. In this particular case, we're looking at an aggregate measure of implied volatility. So what we see here is not just implied volatility, that is what traders were pricing options at in a forward-looking sense, but we're looking at that measure over time. It's very interesting. So at this point in time right here, traders were pricing volatility at 0.29, so roughly 29%. And then at this point in time, they were pricing it at 18%. So all of those measures are point in time. That is a point in time measure for implied volatility. At that point in time, the forward-looking consensus was, let's say in this case, 23%. Whereas the green line is saying, hey, returns have already happened. Now let's compute a measure of backward-looking volatility, historic or realized volatility. And what do you notice about these two processes? Well, they tend to be more or less correlated in different cases, different settings. And what we typically see is this idea of a volatility risk premium. Typically, fear drives volatility. And we see a systematic mispricing. We tend to see systematically that implied volatility realizes less than implied volatility would have suggested. So let's say the 30-day forward-looking implied volatility is 30%. If I was to run a regression in a forward-looking setting on the average realized implied volatility, I would tend to see on average, yes, it certainly does decline. And I'm going to put my money where my mouth is. I actually produced these regressions for you here. Y equals X is suggesting, hey, the implied volatility in a forward-looking sense was measured correctly. So if the slope of the regression line was 1, then implied volatility would certainly perfectly predict the subsequent realized implied volatility in a forward-looking sense. But that's not what happens. Our regression line actually has a slope that's less than 1. What that means is at any given time we observe, hey, the volatility in a forward-looking sense, the implied volatility, tends to realize lower. Wow, that's pretty substantial. If we break this up into two separate regimes, what I'm going to do is break this up into a low volatility regime and a high volatility regime. We can see at this intersection, I solve that system of equations, I produce two separate regressions. The effect is even more pronounced in the high volatility regime than it is in the low volatility regime. The slope is even less than the low volatility regime. And that is precisely the point that I'm trying to make. So if we go back here, we can see, yeah, the correlation between realized and implied volatility. Maybe there's some sort of relationship here where as things tend to heat up, realized volatility gets higher and implied volatility gets higher. As uncertainty and fear both increase, both measures are likely to increase. That'll increase this rolling correlation. But in general, if we look at it in terms of just implied volatility, we're really focusing on this forward-looking measure, then we can see, yeah, well, on average, people tend to, what? Overprice fear. We've talked about this a lot on this channel. It's not a crazy idea. And this is a very simple regression to suggest why that is the case. Well, yeah, this certainly does not track the y equals x line. This is only a 5-day forward average as well. And in these two separate regimes, we can certainly see that volatility realizes less on average. So what are we trying to model with ARCH and GARCH, implied volatility or realized volatility? Well, we have the Black-Scholes model. We can produce an implied volatility right now. We want to get a sense of realized volatility in a forward-looking sense. And we want to be able to capture dynamics like this in the context of realized volatility. That's what we're building towards here. So when we go about applying an ARCH or a GARCH model, really what we're doing is we're looking at trying to measure some sort of realized volatility in a forward-looking sense. We're trying to model it as some sort of expectation, and that's what we're going to be doing. We're going to be fitting our ARCH or GARCH model to not the implied volatility, but rather the realized volatility. Even with the Black-Scholes model, if it isn't immediately clear why we are fitting an ARCH or GARCH to realized volatility instead of implied volatility, bear with me. It'll make more sense when we get down to the formal definition of each model. Until then, we have to flesh out more dynamics of realized volatility. We talked about implied volatility a little bit here, but what are some components of realized volatility and returns that such a volatility model would have to capture? If we don't understand what we're observing in the market and data, then how can we construct and understand a model to forecast such a feature that we can't even observe? So we'll start with this idea of kurtosis. When it comes to kurtosis and stock returns, typically we're dealing with something called a leptokurtic distribution. That means that the tails of the distribution, so the extremes, are fatter than a typical Gaussian normal distribution, a bell curve. And the problem with that is if you use a normal distribution to model returns, you're going to be underestimating the extremes on either case. And naively, if you're trying to compute maybe portfolio risk, maybe a value at risk, the first thing we'll teach you in some sort of finance class in college, maybe it's just a vanilla finance class and there's no formal study of the implications of such assumptions, you will just approach the risk measure parametrically. You'll take a normal distribution, compute the average return and the variance of that return, the standard deviation, the volatility in a backward-looking setting, and then just plug that into a normal distribution to come up with your risk values. That is not at all appropriate. That's not at all appropriate for so many reasons. Well, what are some reasons? We know volatility changes over time. Case 1, super inappropriate risk measure. Case 2, we observe fat tails. If we try to use a normal distribution, we're underestimating tail risk. And that's what I have here. So this isn't as insulting in this particular case, but sometimes kurtosis can get 10, 12, 15, 18, 20 plus. What does that mean for our risk? Well, the purple is a normal distribution, what your professor in finance class would have you use for a risk measure, and the green is an actual return distribution. But look at the extremes. The purple line dips under on both sides of the chart. You're always going to be underestimating risk on the upside and the downside. That's what it means to be leptokurtic. That's what it means to have excess kurtosis. This is a feature that we observe in almost every single asset. We observe this in stocks in particular. These tails are tremendously fat, extremes on both sides. Hopefully now you're starting to see why we need a model capable of capturing this kurtosis, this excess kurtosis. If we just used the purple distribution, the normal distribution, we would be severely underestimating risk. By how much in this particular case? Well, I've computed the value at risk, and you can see there's almost a 20% difference between the parametric approach with the purple line, something your finance professor would have you do, and the data that we observe, that is this green line. So clearly, we need some sort of volatility model that is going to capture the idea of excess kurtosis in the return space. Because if we're going to try to construct a model to forecast volatility in a forward-looking sense, then aren't we going to want to capture the dynamics of the returns that we're basing the volatility measure on? Certainly, absolutely. And that is largely why the Arch and GARCH model is so impressive. The ability to capture in such a parsimonious way a lot of these stylized facts, and more that we're going to talk about in a moment. Something I wanted to note in this context of kurtosis is you'll hear news outlets cite events as, X sigma events, referencing how many standard deviations away from some sort of mean quantity the event in discussion is and how crazy unlikely it is. But it's kind of ironic how often these, 6 sigma, 10 sigma, 30 sigma events actually happen, right? And effectively, a lot of the time, we're just underestimating this tail risk. They're just throwing this into some sort of Gaussian measuring a mean, looking at historic data, like we did in the beginning to compute realized volatility, then measuring a deviation from that volatility. There's so many ways to construct an inappropriate benchmark. A 6 sigma event may not be as outrageous as those outlets are citing. So yeah, there are a lot of implications of these stylized facts that we are observing and analyzing together. And clearly we're going to want some sort of volatility model to capture these dynamics that we're observing. Some more stylized facts of volatility for you. Volatility clustering. Periods of high volatility tend to cluster together and periods of low volatility tend to cluster together. This means volatility shows persistence and autocorrelation. This is not a crazy idea. I've used the analogy of a boat on this channel a whole bunch to explain volatility, right? You're sitting on a lake. The lake is super calm. You're chilling on your boat. Everyone else is chilling on their boats, and it's flat calm. Then all of a sudden, you see somebody start driving away. Okay, well, why is that guy driving away? Then you see someone else driving away, and someone else, and the water's starting to get choppy. Maybe you should drive away, right? You start driving away, everything gets crazy choppy. That's a volatility cluster. Eventually, everything normalizes and things get glass calm again. But that's this idea of volatility clustering, and that exact same logic can be used for sell-offs in the market. Why is that guy selling? Why is that guy selling? Do they know something I don't? Let me pull out too. Let everyone pull out. Then all of a sudden you're in a free fall. So, that's this idea of volatility clustering, stylized fact. Moreover, we have this idea of mean reversion. Volatility clusters, but it also tends to revert back to a long-run average level over time. Extremely high and low volatility periods don't persist indefinitely. Very easy way to verify this is just to look at a chart like the VIX. S&P 500 implied volatility, that is the implied volatility on SPX options. You can see that it's not up and to the right. It doesn't look like Apple or Nvidia. It constantly reverts down to a mean level. It's behavior you would expect to see from this latent volatility measure. In that case, it's implied volatility, not specifically realized volatility. We also have this so-called leverage effect. Volatility tends to increase more disproportionately after negative returns compared to positive returns of the same magnitude. This asymmetric response and, this idea that vol increases more with negative returns coincides with everything we've discussed about fear driving volatility, the volatility risk premium. That's the so-called leverage effect. We already talked about heavy tails, indicating more extreme events than expected relative to a normal distribution, the impact in news outlets and risk. There's also this idea of long memory. Some studies show that volatility shows a long-range dependence, meaning past volatility very, very far in the past at extreme lags can influence future volatility. Suggests that maybe even in pricing, rough volatility models might be more appropriate, like a fractional Brownian motion, some sort of Volterra process. I have a website, a Gaussian cookbook on this if you want to check this out. But other literature suggests that the evidence is ill-founded, so on and so forth as it goes in the quant finance space. In the charts here, I just have a simple example of some of these stylized facts. I have this mean reversion. We can see this red dotted line as some sort of mean that the volatility process is reverting to. And this is just the 20-day rolling realized volatility. Whether or not this long-term average actually stands is subject for discussion. Again, it's going to depend on your sample, the window you choose, that could change over time, so on and so forth. You can also see the leverage effect to some capacity here. if you look, you can see the volatility change and the previous return. And on the positive side, you can see what? We see declines that are maybe minus 0.06 versus the negative return, which has an increase of 0.08 at the max there. It's an anecdotal example, but it still exhibits the leverage effect. The decrease in volatility from positive returns is less than the increase in terms of magnitude from negative returns, and that is the so-called leverage effect. So 2 stylized facts visualized for you here. Clearly all are very important, and our model should capture in a parsimonious way as many of these as possible. So if all of these dynamics are important to capture in a volatility model, what did they do before GARCH Models and Engle's research? Well, clearly they weren't able to capture excess kurtosis, this idea of volatility clustering, heteroskedasticity in one single parsimonious model. Sure, there may have been ways to capture those dynamics, but you always have some sort of complexity efficiency trade-off when it comes to modeling. So we always want some sort of parsimonious representation that's capable of capturing these dynamics in a very efficient way. And that is exactly what the GARCH model does. Let's break down GARCH models step by step to fully understand them and appreciate the dynamics that they capture. So let's start with what an GARCH model is. Well, it is an autoregressive, conditionally heteroskedastic model. It is a class of models that is going to go about capturing the dynamics that we observed above in the data, particularly for volatility. Okay, well, what is autoregressive? What is conditionally heteroskedastic? Autoregressive just means we're using past values, the model's own past values, to estimate future states. Anytime you see auto in a time series capacity, you're typically dealing with a process's own lagged values. Auto covariance, auto correlation, so on and so forth. What about heteroskedastic versus homoskedastic? Well, this is particularly important because this is dealing with variance or volatility, standard deviation. If a model is homoskedastic, it proposes a constant variance. We never see this in finance, right? We don't have this wonderful simplifying assumption. If we assume constant variance, then we are making an assumption that we know is incorrect, and we've already observed this in the data in an implied volatility sense and in a realized volatility sense. So what about heteroskedastic? Well, if a model is heteroskedastic, it proposes that this variance volatility is not constant. This is certainly more in line with what we've observed in the data above. We've observed paths of volatility that change over time. It's not a straight line. Specifically, this model is conditionally heteroskedastic. That is, the variance of errors in a model change over time and is dependent on past information. This is quite useful here for volatility. Let's now talk about the actual definition of the GARCH process. We have this return series. So we have y sub t is equal to some sort of mean value for the return plus some sort of error, this epsilon, and this epsilon is time varying. This epsilon is defined as the product of some sort of measure of volatility times an innovation. And this innovation is assumed to have a mean 0 and a variance of 1. Often this is standard normal, but other heavy-tailed distributions, other extensions are also relevant. So this is the process for returns and errors. What about the volatility process itself? Well, hopefully now it's starting to become more clear why we were using the realized volatility, not implied volatility. We are looking at this sigma squared term here. And what we're doing is we're saying that this volatility, this realized volatility, is equal to alpha sub 0, some sort of intercept, some sort of level, plus alpha 1, which is going to be a coefficient, on some sort of lagged error value squared. And if we look back at the definition of this epsilon, well, it's defined in terms of sigma. So effectively, it's sigma squared times z sub t squared if we plug that on in here, but at t minus 1. Okay, and that's where the autoregressive component comes in. And the number of terms that we are extending to is based on the order of the process. So we go t minus 1, t minus 2, all the way to t minus q, and that is our ArcQ model. If it was an ArcH1 model, we would just go out to this one term here. Now we'll talk about the conditional and unconditional expectation invariance in a moment, but before we do, let's just see this model in action. I am going to horse race this model against something that doesn't capture the volatility dynamics we observed above, an exponentially weighted moving average, and I'm going to naively use that to try to forecast realized volatility. So we know that that model isn't going to capture the dynamics that we want, this excess kurtosis, the leverage effect, volatility clustering, things of that nature. So what does this look like when we try to fit the model and compute the out-of-sample performance? Well, I'm doing a grid search on both of these models. It's far from a perfect modeling contest. Nevertheless, I'm fitting the models in a similar capacity, so it is a reasonably fair comparison. Here I have a root mean squared error of 42% roughly, and an R squared value of 5.12% for this exponentially weighted moving average. That is really all it's doing is it's trying to use the previous value at some sort of decay factor going back a certain number of lags to predict, or shouldn't say predict, but forecast the next realized volatility. And you can see really it's just trying to chase these spikes, and we get a massive root mean squared error. I also fit an ArcH1 model. It appears to be maybe a little more reasonable in producing a volatility forecast, and the out-of-sample performance metrics would certainly suggest that is the case. We could see a root mean squared error of roughly 25% here relative to the 42% of the EWMA process there, and a higher R squared, so a higher variance explained as well. Now, of course, this is just one example, right? I could overfit the weighted moving average and maybe make it perform better. Maybe I could do the same with an ArcH model. The innovation is really in its ability to capture the dynamics of interest that we were discussing earlier in this video. The stylized facts of volatility, right? The volatility clustering, this excess kurtosis, so on and so forth. And that's why its performance is significantly better in terms of measuring risk, in terms of measuring volatility, forecasting volatility, so on and so forth, because it's actually accounting for those dynamics. Something like a weighted moving average is just going to be chasing previous values. It's just trying to use some sort of weighted combination of lagged values to produce a forecast. Whereas an ArcH model is actually trying to consider all of these dynamics when it produces some sort of forecast value. That is why these models, the ArcH, the GARCH, the generalized extension, is so innovative, so productive. So how do we know that this model is actually capturing those dynamics we discussed earlier? Well, we can actually run the statistics on the model directly. We've defined it above. Now we can take a look at the conditional variance and the kurtosis. So if I have some sort of filtration, I'm going to have information up to t minus 1. I can compute the conditional unconditional expectation. I get 0 in both cases. What about the conditional variance? The conditional variance, given this filtration, is actually equivalent to sigma squared sub t. It's not a constant value. Now it's time dependent. That is very substantial, right? That is this conditionally heteroskedastic component. We're saying, hey, let's multiply this value with some sort of innovation. That's how we've defined this process here. This sigma sub t times z sub t. And that is what makes it conditionally heteroskedastic. When we take this product, if this is some standard normal random variable, then we're not dealing with what? A normal distribution with a constant variance, like this parametric approach. Instead, the variance is going to depend on time t. That is substantial. So now all of a sudden, it's a series of Gaussians, if we're using that for our z sub t innovation, with time varying variances. And that is what is going to help us account for those fat tails. That is what is going to help us account for that excess kurtosis. And that is why this is so substantial. So when we come on down here, we see, hey, we certainly are conditionally heteroskedastic. We can see the unconditional variance being some sort of function of the alphas in the definition of the ARCH process. But the distribution itself is leptokurtic since, again, like I said, it's a combination of a series of Gaussian innovations with different variances. How do we know this has excess kurtosis? Well, we can just go about computing the kurtosis value. And if we do that, we can see this exists when, so long as we don't have 0 in the denominator, and we're not dealing with some sort of negative value, and we have a value greater than 3, there will be fat tails. So we can actually ensure mathematically, given some sort of fit, that we are accounting for this excess kurtosis observed in volatility in the data. So where does the GARCH model come into play? Boleslav 1986, a bit after Engle's seminal research, we get this generalized autoregressive conditionally heteroskedastic model. Why not just use an ARCH model? Why use a GARCH PQ model? Well, you can see the dynamics are roughly equivalent, right? We still have this return process. We have this epsilon, this error process, some sort of innovation scaled by some sort of a variance that changes over time, right? It's time dependent. Great. It's capturing that dynamic we observe in the data. And we look back to this volatility process. We see, okay, we still have that series of alphas and the epsilon, those innovations with the time varying volatilities. But we also have this new term here. So we're not just looking at lagged squared residuals. We're also looking at lagged conditional variances. So we're including this new component in the overall process. Why is this better? Well, mathematically, we can show that an ARCH infinity model, that is, if I go back up here and I look at my ARCH model specification and I include infinitely many terms, that is equivalent to a GARCH 1-1. So if I have an ARCH infinity process, I can rewrite this in this way. I can multiply this second equation by beta. I can subtract it from the first equation. And then if I rearrange, I get a GARCH 1-1 process. So an ARCH infinity process can be represented as a more parsimonious GARCH 1-1 process. So in other words, we can capture the same dynamics in an infinite ARCH process as a simple GARCH 1-1 process. That is absolutely wild. The cool thing here is if the GARCH model is a more parsimonious ARCH and an infinite order ARCH process captures volatility dynamics we're interested in, then certainly a more parsimonious representation in this GARCH model will also capture those dynamics. And that is exactly what we see. I've also implemented a GARCH 1-1 in a similar capacity to the weighted moving average and the ARCH model above. We get a higher errata sample R squared and comparable root mean squared error to the ARCH 1 model. It's going to be sample dependent, but largely, of course, we can confirm mathematically that yes, GARCH is going to be the way to go, as we don't need an infinite order ARCH model. We can just simply use a GARCH 1-1, and that is widely used in practice. So yes, the GARCH model definitely has similar benefits. It captures this volatility clustering, models excess kurtosis. It has a time varying conditional variance. And really here, it's going to require fewer parameters, capturing long memory dependence through the beta term. So unlike ARCH, which has, this infinite order that you would need to capture those dynamics, we can capture that through this beta term. I think it's also worth noting that what we've seen here is a very low explainable power in the ARCH and GARCH models, but this is particularly expected for single stock equities. So if we look at the R squared here, we get less than 10%, and we get 8% in this case, and I think it was roughly 5% in this case. So GARCH at 8%, ARCH at 5%. It's really to be expected Intraday returns are actually a better representation of the latent volatility process, and GARCH can explain up to between 40 and 60% of such variation, as documented in the literature. So if you're interested, I highly recommend you check that out or try it yourself. This is a really cool result, but maybe not all that unexpected. Here what we're doing is we're looking at intraday returns to help forecast the daily volatility. So maybe 5-minute increments, and we're using that to help inform the daily volatility forecast. And if we are getting a better representation of the latent process using this intraday data, and our model effectively captures the dynamics of that latent process, then I certainly would hope we see a significant amount of variation explained, and it does appear to be the case. As I had said earlier, highly recommend you check out the literature on this topic. Some models can even outperform this. It's going to depend on the sample too, but a very, very cool result. A very simple way to see the profound impact of such an Arch or GARCH model is through portfolio risk management. You can use a lot of different trading examples. You could talk about some sort of quantitative trading strategy where you have a series of vol forecasts, maybe use some sort of compression like PCA to extract common variation of all of those vol features into one feature, and you do that for a series of signals. That's more of like a quant trading application. Maybe you look at not just volatility forecasting, but maybe in terms of option pricing. There's a lot of different things you could do with this model, but one of the easiest ways to see the profound impact in being able to capture these dynamics is by looking at a naive value at risk, something your finance professor might have you do, and a GARCH value at risk, and you can immediately see the significant difference. So what I'm going to do is I am going to take this traditional parametric approach to measuring my portfolio value at risk. This is equivalent to roughly what we did up here with this purple distribution. I'm going to assume that the volatility is constant, right? This homoskedastic assumption, which is certainly violated in practice. And what I'll do is I'll use that to measure my value at risk. And what that does is it gives me a threshold. And if I'm measuring, say, maybe a 5% exceedance threshold, then I'll expect to see that exceedance threshold proportionally broken 5% of the time. Okay? Now, this is a naive measure with assumptions that are violently wrong. What do we actually see in terms of exceedances? I see 40%. 40% in that homoskedastic setting. Okay? Now, what if I correct a lot of those violated assumptions? I'm going to use a GARCH model instead. So I apply a GARCH model. Now I'm getting something much closer to reality, right, that I'm looking for. I get 9.74 exceedances relative to that 5%, which should be expected. Certainly significantly corrected. We may be able to capture this better. Of course, there are different things we could do to improve this. This is just a simple horse race between a naive approach with a homoskedastic assumption and this conditional heteroskedasticity offered by the GARCH model, and we can already see a significant improvement in our risk performance. We are far better capturing potential downside using this GARCH model than we are a naive parametric approach. Too long didn't watch. Here's your executive summary. Volatility is an unobservable measure of variability in the return space. We can proxy for volatility in a backward-looking sense using historic or realized volatility on past returns. We can also look at volatility in a forward-looking sense using implied volatility, though that comes from a completely different source, that is the Black-Scholes model. There are many stylized facts about volatility, including the leverage effect, volatility clustering, excess kurtosis, this leptokurtic return distribution, and all are important to capture in one parsimonious model. Naive parametric models fail to capture these dynamics and can severely underestimate tail risk, as we've observed herein. Engle proposed the GARCH model, this autoregressive, conditionally heteroskedastic model, which is capable of modeling these dynamics, which improve forecasts and risk measures. We then got this generalization from Boleslav, this GARCH model, which is a more parsimonious arch model, can be represented as an infinite order arch model, can capture richer dynamics with fewer lags, quite impressive. And these vol models outperform others that do not account for these dynamics, especially in the context of risk modeling, as we saw in that value at risk example. Some future topics, things I'd like to talk about. This list does just keep getting longer and longer. I kind of love it. Some extensions maybe to Arch and GARCH models and applications. We really didn't talk about a lot of the literature, valid metrics. We didn't talk about Q-like. We talked about RMSE, R squared. We could say whether or not those are valid. That's subject for discussion. But those are more technical niche videos. I'm not sure what the interest is in those particular topics. Maybe I'll write an article and post it to Medium or my blog. Kalman filters, other time series analysis techniques. I'd like to continue with these ideas, maybe even bake them into a live system. So using interactive brokers, maybe some sort of GARCH for intraday vol and Kalman filter for live pricing. That could be an interesting project. I'd also still like to build this earnings event options trading dashboard from my video on trading implied volatility crush. So be on the lookout for that quant build. Lots more quant builds in the future. Those are some of my favorite videos to create. More in the stochastic calculus space, deriving and solving the Black-Scholes equation. This was to get back into understanding option exposures theoretically, where they come from, understanding the Greeks, risk management, so on and so forth. And this plays nicely into the calibration of stochastic models to go about extrapolating exotic prices. That's a very necessary component, is understanding where these pricing PDEs come from theoretically in terms of structure and argument. I know we've talked about pricing exotics in the past, and I still need a dedicated video on the calibration of such models to a market implied volatility service. I actually just finished 2 scripts, one in Python and one in C++, calibrating a Heston model to market surface. So it's essentially institutional grade calibrators. So I would like to do a video on that topic, and that extends naturally into neural networks, machine learning, to approximate pricing functionals, and that is useful again for calibration. And then of course simulating those relevant stochastic processes, maybe the rough model family and Volterra processes, to get at this idea of rough volatility. More niche topics, but I certainly would like to create videos on those in the future. And that's going to do it for this video on the Arch and GARCH models. I hope you enjoyed. I hope you learned something. Again, these videos certainly take a lot of time to create, so if you enjoyed, please like, comment, subscribe. Check out channel membership. If you'd like to master your quantitative skills, check out quantguild.com. Other than that, thank you so much for watching, and I will see you in the next video.